Hello everyone, I hope you're doing well. In this video, we are going to solve this question, the part 1 of this question. The problem says that the cobalt has a hexagonal structure and the lattice parameter are as follows. The lattice parameters are given to be A equals 0.25071 nanometer and C to be 0.40686 nanometer. Okay, in part 1, it says that the atomic mass of cobalt is 58.93 grams per mole. Calculate the density of cobalt. So in this part we have to calculate the density of cobalt, and the lattice parameters are given and the atomic mass is also given. So let's start with the problem. The part 2 and 3 will be uploaded in separate videos. It is because each part is unique and different from the other parts, and sometimes the problem becomes very lengthy. So I link their solutions in the comment section when they are uploaded. Okay, so stay tuned for those parts also. Let's begin with the first part. Now we'll first write the data that is given, which is A equals 0.25071 nanometer. Okay, nanometer means 10 raised power minus 9 meters. Okay, and similarly C is equals to 0.40686 nanometer. Converting them into SI units is very important. Okay, all right, and the molar mass or the atomic mass is given. I am representing the molar mass with capital M letter, which is given to be 58.93 in gram per mole. Okay, and we have to convert it into SI unit, which is kg. Okay, for mass it is kg, not grams, as SI unit. So K means kilo, which is a prefix called as 10 raised power 3. Okay, equivalent to 10 raised power 3. So to produce 10 raised power 3 here, we'll do this one thing, as we'll multiply with 10 raised power minus 3 and also multiply with 10 raised power plus 3, so that the equation remains neutral. Okay, so 10 raised power minus 3 remains as it is, and in place of 10 raised power 3 we can write K, which is kilo, and G per mole is similar, is as it is. So the molar mass is 58.93 multiplied by 10 raised power minus 3 kg per mole in SI units, and we have to calculate the density, volume density for cobalt. Okay, now we'll move to the solution. Okay, and for solution we'll first write the formula that we are going to use, and it is also mentioned that it is having a HCP structure, so we'll consider the HCP unit cell here for finding out the density. Okay, we'll use the property of the HCP unit cell in order to find out the density here. So the volume, we know that the volume density is given by rho equals mass of the unit cell. Okay, because we are considering here the unit cell, so we'll consider the mass of the unit cell and the volume of the unit cell. We know that the density is usually given by the mass of the thing divided by the volume of the thing. So here we'll consider the unit cell of HCP, the unit cell of cobalt, which is HCP, and its unit cell. So here we'll consider the unit cell of cobalt in order to find out its density. The density of cobalt is equal to the density of its unit cell. Okay, so it is a property of the crystalline solids that its density remains invariant, or in other words remains constant. So the density of the whole crystal will be equal to the density of the single unit cell. Okay, so that is why we are using that one property of the crystalline solids, and the density will be given by the mass of the unit cell divided by the volume of the unit cell. In the unit cell we know that here it is HCP, so let us denote it as equation number 1. So now the mass of the unit cell is actually given by the can be written as since all of the atoms are identical. Okay, in HCP, in the unit cell, for example, all of the atoms are cobalt atoms, that is why. So we can write it as we may take the mass of one cobalt atom. Okay, one cobalt atom, and multiply it with the number of cobalt atoms per unit cell. Okay, it is similar to saying that if we have 5 toffees similar toffees, and if we know the mass of one toffee, okay, which is, let's say, m, okay, and if you want to find out the total mass of the 5 toffees, then what we will do is to simply multiply 5, which is the number of the toffees, with the mass of each toffee, and in that way we will get the total mass of the toffees. Similarly, if you want to find out the mass of the unit cell that is made up of cobalt atoms only, then what we will do is to count the number of cobalt atom that that unit cell has, okay, and we will multiply it with the mass of each cobalt atom. In that way we will get the total mass of the unit cell, which is made up of those cobalt atoms. So in general, mass of any atom is given by its molar mass divided by the Avogadro's number. Okay, molar mass or atomic mass, they are the similar things. So molar mass is given and Avogadro's number is a constant. We know that 6.02 multiplied 10 is power 23. So we'll simply put it right there and multiply by the number of atoms per unit cell. In HCP, you can remember it is 6. Okay, there are the 6 net atoms per unit cell in HCP. So we can calculate it right here by putting the value of molar mass, which is 58.93. You need to put the values in SI units, okay? And 6.02 multiplied 10 is power 23 is the Avogadro's number. So let me calculate it and get back to you. And I will get back to you. So this is what we got, 5.87 multiplied 10 is power minus 25. So yes, this is the mass, minus 25 kg. All right, and now we need to find out the volume of the unit cell, volume of the unit cell, HCP unit cell. So the volume of HCP is actually the area of the basal plane into the height, which is actually C. Okay, for this is the general formula, and I don't think so that you should know the very details of how that formula is obtained. Okay, that is why I'm not mentioning it right here. All right, so the area of the basal plane means that one plane which looks like that. Okay, this is familiar to you, okay, and it is raised by C units along the z-axis, which defines its height. All right, so you can see here that this basal region contains 6 triangles, 1 2 3 4 5 and 6. So we find its area, total area of the basal region, by multiplying that 6 number with the area of each triangle, and area of each triangle is actually 1/2 a square sine of 60 degree. Okay, each of these triangles are equilateral triangles with 60 degree right here. Okay, this length is a, this length is a also. Okay, and this is the property of HCP structure, that these all lengths are equal to each other. Okay, while the C length is not equal in HCP. Okay, this is the property of this structure. Okay, that these lengths are all equal to each other, but the length along the height is not equal only. So yes, this is the area of the basal region, and it is multiplied by the height. Height is C simply. So 2 into 2, and this is cancel out to be 3. A square sine of 60 degree is actually under root 3 by 2 into C. So it's 3 under root 3 a square C by 2. Okay, and this is the volume, and let us put the values right there in order to get the volume. Here A is 0.25071 multiplied 10 is by minus 9 square into C. C is 0.40686 multiplied 10 is by minus 9. Okay, let me simplify it, let me calculate it, and then I'll get back to you people. So this is the expression for volume that we have got after calculating that thing. So now putting the value in equation number 1. Now we know the volume of the unit cell and also the mass of the unit cell, so we can get the density of the cobalt's crystal, or density of cobalt, as the mass of unit cell is 5.873 multiplied 10 is power minus 25, okay, divided by 0.06644 multiplied 10 is power minus 27. And let me simplify it and I'll tell you what result I got. So this is the final result that we got: 8839.55, 8839.55, since its density in SI unit, so it's kg per meter cube. Okay, this is the final result that we got. It can also be written as, if we take this 0.3 units, okay, backwards, so it will become 8.839 multiplied 10 is power 3 kg per meter cube. If we move backward, then the power will be positive. If we move forward, then the power will be negative. Okay, so the process is reversed. For example, if you move backward, the power will be forward, means positive. So yeah, that is the result.